I would like to tell you something about a single emitter emitting into the beam emitting resonance fluorescence into coherent probe beam, which is essentially an interference experiment and with single atom. There has been some single emitter interference experiment. Mostly they use this configuration where you have your excitation beam, your single emitter, and then you collect the scattered field, combine it with some coherent field, and you have some detection scheme that can be something like HBT detection scheme. For example, in Cambridge, they measured a G2, and by tuning the relative phase between the laser and the emitted field, they measured that the coincidence rate can vary based on the introduced relative phase. However, question is, what would happen if the emitter was already in the same mode as the laser beam? Or more graphically, what if we take the laser and put it over here? This is exactly what was, or more or less exactly what was proposed by Daniel Goncalves, who's been a student at ICFO as well in Derek Cheng's group, just 2 floors above our lab, which shows you that the theory transfer can be very short distance temporal physically, but can still take some time temporarily. So what we're going to be looking at is our detected field, which has consisted of our input field and the scattered field from the atom. And our transmission is just the ratio between the detected field and the input field. If we don't have any pump, then our transmission is given by a single parameter, which is the coupling efficiency. And this is the geometrical ability to focus light onto the atom. And it is simply given by the lenses we are using. However, if we turn on the pump, the form of the equation doesn't change. What changes is the coupling efficiency parameter, which goes from the eta to become lambda. And lambda is our effective coupling efficiency, which is given by our geometric coupling efficiency and the ratio between the total field and the probing field, where omega denotes the Rabi frequency introduced by the fields, either a total field or one of those pumping or probing field. And we take into consideration that they have some relative phase between the pump and the probe. Firstly, let's put that phase to 0 and look at what would happen if we vary the pump-probe ratios. And what we get is we can actually vary the transmission, and we can tune the transmission from going to complete extinction if we tune the effective coupling efficiency to 0.5. But if we actually go with too strong of a pump and our pump probe ratio is very high, we get into a regime where our coupling ratio can go above 1, and then we will see a boost in our transmission, which is slightly weird. And this has also implications for the G2 correlations. So if we look at the G2 and we are very close to this regime, then we expect to get a strongly bunched light from a single emitter. And once we go over 1, then the field we detect will be dominated by the scattered field of the atom. Therefore, we get the anti-bunched light as we would expect from a single emitter in free space, which is great. However, as I said, this has also a phase component to this. So if we start varying the phase, we can see that the transmission actually varies with it. So if we have the pump probe ratio of 0, which is our benchmark, which means the pump is off, we have no relative phase, and therefore we do not expect to see anything. But once we start turning on the pump and increasing its power, then we get to see that for phase equal to 0, our transmission goes slower until it reaches the inflection point and then starts increasing again. But if we have very bad phase definition and we might drift all the way into here, we never see a decrease in transmission. We only see some increased transmission because we have constructive interference at that point. Let's look at the study case of pump probe ratio of 4, simply because it fits very neatly into our plot. If we look at this statistically, so if we sample from this with uniform distribution, it leads us to arcsine probability density function, and we can easily define minimum and maximum transmission. And these will become important if we want to reconstruct the phase from our transmission measurement. And if we add some noise on top of this, what happens is that in our sampling, we need to convolve these two probability density functions. So our our distribution becomes the convolution of arcsine and normal probability density function. And what we get is this two-lobe distribution structure. Internally, we tend to call this curve the Batman curve. And however, where do the noise come from? Mostly this noise comes from our atomic movement. So a trapped atom in the trap, it still experiences some non-zero locality. It is not a point source. It just moves within the trap, and it has some center of mass distribution. So as long as we can keep the atom on this axis, it is going along with the propagation direction of both beams, and it does not experience any phase change. But it won't do that. It will just diffuse in some volume over here, and if it leaves the diagonal, then it experiences path difference between the pump and the probe, and therefore experiences a phase change. And from what Daniel Goncalves showed us, we expect that we need the localization of the atom to be better than lambda over 4. However, we need to be very careful because this is a resonant scattering, and resonant scattering heat up the atom. So we need to keep the temperature of that atom as low as possible to keep the atom localized enough. How to put this in the lab? First, we need some trapping system. So we have a multi-cross geometry trap with 4 high numerical aperture lenses. Through a pair of those, we send a far-off resonance trap at 852 nanometers, and we overlap the trapping region with our magneto-optical trap at 780 nanometers, and we let the atom enter and leave the trap as it wishes. We use the rubidium-87 atom with the cooling on the 2 to 3' transition and repumping on the 1 to 2' transition of the D2 line. And our trap waste is approximately 1.3 micrometers, and the atomic temperature after cooling is around 20 microkelvins. In order to implement this scheme, we've decided to put the probing beam orthogonal to the trapping axis, and the pumping beam we decided to go vertically. So we do not focus this beam, but we can compensate for the loss of coupling efficiency simply by increasing the power. And what we detect is the interference between the scattered field induced by the pump and the probe and the probe field that we send into the detected mode. And we have this interference term as we would expect. Now, we have two things in the interference term. First, we have the average phase, which is the phase a single atom would have. We consider this phase to be stable for a single atom, but to be completely randomized between any two different atoms. And we have this contrast factor, which is given by the variation of the phase, so mostly by the atomic localization. And this scheme also allows us to have well-defined quantization axis, so we can optically pump the atom into the stretch state. Now, as I said, heating is an important element, so let me go quickly through the experimental sequence, because first we need for the atom to get trapped. Once it gets trapped, we pre-cool it. We need to ramp down the magnetic field to reach the minimum temperatures possible. Then we cool it a bit more, just so we're sure that we have the minimum temperature for the experiment possible. We then ramp the magnetic field up, so we get good optical pumping. We turn on our pump probe scheme and we measure, and then we turn the magnetic field back down. In order to get as much signal from a single atom as possible, we repeat this sequence of the cooling and measuring 80 times. This is limited by the pump probe stability of the lasers, the phase stability of the laser, and the atomic lifetime in the trap. And once we're done with this, we check if the atom survived. If it didn't survive, we just scrap the data. And we collect a probe signal, so we collect our input field for the equivalent time as our measurement time. If we look at this in the real time, so on your x-axis, you have the time of the day in hour and a minute, and each point is a single atom. You can see that we have some oscillation between some low transmission mode and high transmission mode. So natural thing to do is to look at the histogram of these measurements, and we can see our distribution that looks that we fit with the convoluted function, and this quite well describes our data. As I said, we fit it with the convolution, and we fit two parameters: the center of the distribution and the half width. And then we extract the minimum transmission as the center minus the half width. And by varying the pump probe ratio, pardon, the ratio of the probe photons we send and the scattered photons we collect of the atom, we can vary the minimum transmission of the probe. And our record so far is 82%, which is significantly lower than what we would get without the pumping field. In summary, firstly, I showed you the proposed pump probe scheme, and I showed you how we implement it in the lab with our Maltese cross geometry trap. I showed you our very recent data and some early stages of the data processing. And currently in progress, we are measuring the spectrum of the pump probe scheme, so the spectrum of the transmission. We want to optimize the probe extinction, so we want to go below 82%, and we would like to measure the G2 statistics of this scheme as well. With this, I would like to thank the group at ICFO, and mainly the people that I've been lucky to work in with the group, Laura, Sondas, and Roman, and our group leader, Morgan Mitchell. And I would like to thank you for the attention with one more fit, and this is the fitting of this data with the head distribution, because it looks very similar. Thank you for your attention.
Thank you. Thank you, Thomas. Thank you, Thomas. Now time for questions. Do we have questions? If not, I will ask one question. Can you show this transmission probability as a function of time? Because yeah, it looks to me as there is some periodicity starting from 245. I would fit here the sine curve. Can you explain this periodicity in the data?
Yeah, so the phase variation in here is mostly due to the temperature movement and air pressure changes with inside of the lab, and this is not periodic. It just looks like it, because if we run the measurement when we start the experiment, the oscillations that you see are significantly faster. So this gets slower slower as the measurement progresses throughout the day. It's just stabilization of the system.
Okay. So maybe somebody got it. Yes, we have a question over there.
Just like just like a simple question, like you have a hat, kind of a Batman hat, like so. It's just simply like why there is. So would you like elaborate like why does it
Like-
happen? Yeah, like this. Yeah.
I'm sorry, I'm not sure I got the question.
Sorry, like so why there are two peaks or yeah.
Sure. This is simply that you get the arcsine underlying distribution from the interference.
So yeah, that part I would like to know. Like,
So when you have a trigonometric function and you have a uniformly distributed phase underneath it, if you look at the statistics, you will get two peaks at the +1 -1 region of the trigonometric function, and you will get lower probability of being in here, because there is just the slope of the function is so much bigger.
so you'll get okay. So you get slightly different distribution in the other than the uniform distribution in reality, or
I'm not sure I got that.
okay, then I can ask
We can
later.
talk about it later. Maybe it's better.
Okay. Are there any questions, comments? I don't see. If not, because it was the last talk of the session, but also the last talk of the conference, I will use this opportunity and I will ask you to thank all speakers of this conference, the people who made this conference very successful. They were the speakers, so let us thank all of them.